this video, we are going to try the second part, the part B of the quantum mechanics assignment, one of the assignments that we were supposed to try. And the second part, also part B, consists of two questions where I have tried a few ones. That is the third question and the fourth question. Remember, I had tried the first and the second question in the part A, and here I have already solved a few questions for making the video a short one, and I'll be helping you with the process that has been uh, put in to obtain the results. So this is the third question, which had two vectors over there, that is the psi1 and the psi2 eigenkets, which were represented on the phi1, phi2 and phi3 basis, and we were to find the inner products in the first bit of the question, which I have obtained. You can see for yourself. The inner products are pretty simple because as I've already mentioned in one of my earlier videos in quantum mechanics Hilbert space, uh, the problems that I had made, or that I have uh, done over there, we had discussed that these simply act as you can compare them to the three-dimensional orthogonal coordinate system, and similar to that, the inner product of I with I, J with J, K with K is the same thing, more or less. These are orthonormal eigenkets and orthonormal basis, and then we were supposed to obtain the matrix element of the the operator there, that is the outer product of psi1 with psi2. And in order to obtain that, for each element we take the projection of the eigenket on that basis, and then we obtain, like in this case we have over here 1 1, and for the 1 1 element over there we proceed like this one, that is, and then similarly for 1 2, and this is for 1 3. As you can see, the bases are changing. We are taking the first base over 1 and the second base over 1 for the first, that is 1 1, then the projection on the first basis, and followed by the projection on the second basis for 1 2, and first and third for 1 3, and likewise we follow it up to 3 3, that is the last one over here. So that's more or less the idea of it, and in case you find it pretty tricky, you can always provide yourself with a rough work over here that I have done, uh, because there are repetitions over there, and with results at hand we can calculate them easily, just like I have done over here. So you can check those values and you can put those values so that you can obtain the required or desired result. In the next bit, we are supposed to obtain these two values, that is this one dx, the derivative of the x, that is the position operator, and the derivative of the momentum operator for a particle of mass m in the gravitational field, with the Hamiltonian provided. So this is the Hamiltonian that has been provided, and we have to solve the equations for x at t and p at t, which is what I have tried over here. X at t, we have obtained a solution, because having obtained this value over here, it's we take the second order differential with respect to time, and the solution for that is going to be this one. With the solution, we are provided with an initial condition, which is this one, that is x at t is equal to 0 is going to be x0, and similarly p at t is equal to 0 is going to be p0. Now for this commutation relation that I have obtained over here, because the commutation relation is going to provide some value, finite value, only for these two, that is x with p squared. Now the squared term, that commutation has been obtained over here using this relation, this general relation over here. um, and because x with x is with this x, the x is going to be 0, so that's not going to provide any result. Similarly, I have obtained the commutation relation over here for pH, and that's the value that we get is this one, this much, not that exactly, that is actually this one is the value. Now with, well, that is as you can see, there's a mistake over there, that is x not p, because here we have, for p we obtain x and for x we obtain p, likewise. And this relation that we are going to use, these two things that we have used over there, that is the commutation relation of x with p, and the Heisenberg picture that we have used for that, the relation for any given operator in the Heisenberg picture. This is an operator, suppose h suffixed tells us about the subscripted, tells us about the Heisenberg picture. So any operator in the Heisenberg picture, this relation, this relation that we see is what we have used to obtain these values, this and this, which we were supposed to obtain by using the commutation relation. Just like over here you can see I h bar, partial derivative of x with respect to t is going to give us x with h, and remember x with h is simply h, we have extended that h in terms of p squared and m squared omega squared, because that is what h is over here, the capital H, that is the Hamiltonian. And similarly we have used that case over here as well for the momentum. So I'm going to erase all those black marks that I've just drawn and help you with the process that is involved by allowing it to view clearly. Now the final equations of motion that were to be obtained, that is x at t and p at t, using the initial conditions, that is x at 0 is x0 and p at 0 is p0, that has been obtained. You can refer to the previous page. And then finally we were to obtain the commutation of x and p in time t1. So instead of any general t, we are putting the time as t1, and in that commutation I've just opened that expression for x at t1, p at t1, referring to the solutions that have been obtained just above. And what we see is that commutation relation is going to be for x and p only, the finite value, because x with x is going to give us 0, x with p is going to give us 0. So all we have is x with p in the first case and p with x in the second case over here. You can because I was crunched for space, I had to write it like this. I hope you can write the formula completely in your respective papers pretty well. And the result that I've obtained is simply IH barred, but I can have zoom this for you clearly. So this is the value that we have put over there. This is simply the same value that is right at the top for x and p. Right. So comes out to be IH barred, and that is what I have obtained. You can check for yourselves in case you obtain something else. I'm open for any kind of correction. Now for the first part, the 4a, the two bits that we can try and solve right now is to show the first one is pretty straightforward, is to show the creation operator uh, the proof that we require for it, and we can write it as follows. The solution for that is simply like this. It can go like this. Now the Hamiltonian over the creation operator times of the eigenket operating on the n basis, that is going to give the results as shown, and from that we have the final case where we have n plus 3 over 2 times of h cross omega uh, on the multiplied to the creation operator acting on the basis. Also, we have the Hamiltonian to be acting on n plus 1 to give us n plus 1 plus half times of h bar omega n plus 1. And that is nothing but equal to n plus 3, 3 over 2, the same thing that we obtained in the previous case. Also, we know that the creation operator is an eigenket of the Hamiltonian, and so corresponding to n plus 1, uh, the creation operator has to be some multiple of n plus 1. So we have the creation operator acting on n plus 1 to give us some other value multiplied to n plus 1, that is, we are assuming, let us say, that is bn. So now we have a, that is that's the other way around, the bra vector, and that gives us the conjugate on the right hand side. Now if we multiply both of them, these two, what we are going to get is n a dagger, the creation and annihilation operator, and that is equal to simply n plus 1 bn, the conjugate of it, bn n plus 1, and that is going to give us bn multiplied to bn, and the rest of the term, that is n plus 1, n plus 1, that goes to 1. So we have this as bn squared, right? Now the Hamiltonian can be related to the creation and annihilation operator in this manner, and so from that what we get is uh, if we are to operate the product over n, then instead of that product we can use this relation above, and we get the value of the product from that relation to be equal to h over h cross omega, that is the Hamiltonian operator over h bar omega, minus half. We need not care about the minus half because that's just a number, it's not operating on anything, so that will give us n plus 1 n, and that's because of the creation operator acting on it. Now also we have n a dagger n, that is equal to n plus 1 times of the inner product, which is going to give us n plus 1. Now bn square is therefore equal to n plus 1 because this was resulting in bn squared, and from that what we get is the value of bn to be equal to root over of n plus 1, and therefore we have the creation operator, or the raising operator as you may call it, the raising, then it was named as the creation operator. So that is going to give us the value that we were, or the proof that we were seeking. So as I said, it is pretty straightforward in this case. Before proceeding further, I can provide you with another correction over here. This is a dagger because that's going to act on this, and because this a dagger a plus half over here is going to give me the Hamiltonian on the left hand side. So this will be plus when we take it as a dagger. That is the annihilation followed by the creation, the product. And so that half cannot be neglected actually, because the half is getting multiplied um, with that ket provided, and h is going to give us n plus half. So half plus half is going to yield 1. So that half need not be neglected, as I said before. So the correction to that. And rest of the things are pretty clear. We have the solution as per our requirement. Small changes here and there which are very much essential in terms of the creation and the annihilation operators. Now as far as the second bit is concerned, that is the relation that we had to use, uh, where we had to use this, that is psi n plus 1 x 1 over 2 times of n plus 1 under root, and this is xi minus d over d xi psi n x. Now we had to use this to find psi 3. Now for that, first of all, we can use value of psi 1, that is psi 1 x is simply equal to a over 2 root pi whole raised to the power half 2 times of 2 times of xi e, that is the exponential of xi squared over 2. Now from this, if we use to obtain psi 2x, what we find is, I'm cutting it short for you, a over 2 root pi raised to the power half, so that term comes out, and within the brackets, the square bracket, we have over here 2 xi squared minus 1, and that is multiplied to the exponential of negative of xi squared over 2. And this one, once again, in order to find psi 3 of x, what we do is we proceed in this manner. Now we are taking n as 2 over here, because this will be 1 over root over of 2 times of 2 plus 1 xi minus d over d xi, that is derivative with respect to xi, psi 2x, the value that we have obtained over here. And if we put those values, then what we find is, this is simply, well, that's under root, that is 6, and one of the derivative terms is going to give us a factor 2 over there. So what we are going to get is 1 over root 6, and there's a root pi if I've probably forgotten. Yes, there's a root pi over there, and that is the entirely under root. No, that's the relation. Sorry, that's the relation. My bad. Psi 2 has that value, that is a over 2 root pi entirely under root, that is raised to the power half, and the rest of the terms in psi 2 are that is provided over there. So this xi minus d over d xi of the term that is there, that is 2 xi squared minus 1 e raised to the power minus xi squared over 2, and that is going to give us Well, root 2 and root 6, and I'm tempted to multiply them, so let me do that. So I have a over 12 root pi all under the root, and over here the first of the xi gets multiplied to the 2 xi squared, so that is going to give me 2 xi cube minus the second term is 1, so xi multiplied to 1 is xi, and then we are going to take over the derivative term, which I'm going to keep in curly braces. Well, e raised to the power minus xi squared over 2, that can go as a common term even after the derivative. So we have a 4 xi over here plus, now the second term's derivative, the e over negative of xi squared over 2, that's going to come up once again, and that is well kept within kept out of the bracket. So now we have 2 xi squared minus 1, that is the first term, and the derivative of the second term is going to give us a negative of half multiplied to 2 xi, and we have the exponential term, that is, I'll have to write it over here, exponential, it's multiplied, of xi squared over 2. Now 2's cancel out over here, so we have a minus xi over there, and let's first solve the curly braces, the terms within the curly braces that are over here. So we have a negative xi multiplied to all of that, so that gives us, this will give us 4 xi plus, well, instead of plus, because we have a minus over here and a xi over here, so minus xi, so this is minus 2 xi cube minus of minus xi is plus xi. Now this is within the curly braces. This is 5 xi minus 2 xi cube. When I use the minus sign over there, what we get is a over 12 root pi all under root 2 xi cube minus xi, and this term now becomes minus, well, that is 5 xi and plus 2 xi cube multiplied with e, that is the exponential of xi square over 2. Now this root 12 has 4 times of 3, so 4 can be taken out of that root sign, so we have 2 over there. So this is a over 3 root pi, the 2 goes outside, and we will have a 2 factor over here as well, because this is minus 6 xi and this is 4 xi cube. So instead of 4 xi cube we can take the 2 out, so we have simply 2 xi cube minus, instead of 6 xi we can take a 2 factor out of it, so this is 3 xi e over xi squared over 2, and this 2 cancels out, the 2 that has been taken out cancels out with that 2 outside, so this was the 2 that was taken outside. So all we have left is what is there on your screen right at the bottom, a over 3 root pi under root multiplied to 2 xi cube minus 3 xi, you can take one of the xi's outside, and multiplied to exponential of negative of xi squared over 2. In the next bit B, the first bit has asked us to write down the angular momentum states Jmj for j is equal to 5 over 2, and the eigenvalues of j squared and jz for each of these states. Well, now we'll first have to look at the degeneracy. So the solution, let me use another ink for you, write the solution first. So the solution has, well, first up we have to consider the degeneracy, that is, degeneracy is simply 2j plus 1, which means 2 times of 5 over 2 plus 1, so that is 6. So we're going to have 6 states, and because it is from of 5 over 2, so it's going to be from the negative 5 over 2 to positive 5 over 2 for the mj's. So mj is going to be from negative 5 over 2 to positive 5 over 2, and we'll take these values actually: 5 over 2 minus 3 over 2 minus 1 over 2, then 1 over 2, then 3 over 2, and then 5 over 2. So these are the values, and j is going to be all those states that we have, that is half, 3 over 2, 5 over 2. So let's write them down. Now the states will be as follows, that is states that is in the form jmj. They will be of the form, so first one we have half minus 5 over 2, then we have 3 over 2 minus 3 over 2, then 5 over 2 minus 1 over 2, then the rest of the three states, that is we'll write down the mj's first, and then we have 5 over 2. So these are the mj's, and the j's are going to be simply 5 over 2, 3 over 2, and then 1 over 2, the reverse order. It's easier to write this way. So these are the states. Now in order to obtain the eigenvalues, yes, that we were supposed to obtain the eigenvalues for each of the states of j squared and jz operator. Now the j squared operator is going to give us what's the value in that case? The value in that case is simply j plus 1. Yes, that is the case. So not j plus 1, j plus, yes, j plus 1. So j times of j plus 1 h barred. Okay, so for the first state we are going to get j squared operator on what's the first one? The first one is half. So half minus 5 over 2. So half minus 5 over 2 is going to give us, so j here is half times of half plus 1 h barred squared, and then the state. So here it is 3 over 4, because that's 3 over 2 and multiplied to half, so 3 over 4 h bar squared, half minus 5 over 2. Similarly, we can obtain them for the other states. I'll hope that you can obtain that. And then for jz operator, that is simply going to give us mj times of h bar. So I'm trying another one. So jz operator operating on let's say 5 over 2 minus half, so that state. So for that state we are going to getting the mj in that case is minus half, so that's going to be a minus h barred over 2 of that state, that is 5 over 2 minus half. I've tried 2 out of 12. The rest is up to you for to try. And in the next bit we are supposed to obtain the angular momentum matrix for jy at j is equal to 1. Now for j is equal to 1, we have the eigenkets. Eigenkets to be, we will have 3 of them. We'll take phi 1 supposedly as 1 minus 1, phi 2 as 1 0, and then phi 3 as 1 1. So with those things, that is JMJ for us, all of those, and then the elements are to be written like this, where J prime, MJ prime, JY operator, JMJ. Now this will be non-zero. This is non-zero if we have J is equal to J prime in the first place, and MJ prime is equal to MJ minus 1 or MJ plus 1. These are the conditions for us to have. So that means what we'll be getting as JY11 will be equal to 0, because for 1 1 we'll be having the values as of j's to be like this, like for J11, let me write that explicitly for you. So we will have phi 1 JY phi 1, which means for phi 1 we have this one, that is 1 and minus 1. So this is 1 minus 1 JY and 1 minus 1. As you can see, the MJs are equal. MJ prime is equal to MJ, so that is going to be 0. And that is going to be the same case for 2 2 and JY2 2, and similarly for JY3 3. So the 3 cross 3 matrix that we are going to get, the diagonals are going to be 0. So let's find out what are the numbers that we are going to get. So that actually tells us that JY is going to be of this combination. So if we are taking the delta, Kronecker delta into consideration, so for MJ is equal to MJ plus 1, MJ dash is equal to MJ plus 1, that is going to stand, and for MJ prime equal to MJ minus 1, that is what we are going to consider. Other term will go to 0. It is quite clear that from the relation we can also say that JY 3 1 is going to be equal to 0. So is the case with JY operator, the matrix element 1 3, because 3 and 1, as you can see, phi 1 and phi 3, they carry 1 1, minus 1 and 1 in their the values of MJ, and they are nowhere related as per the given rules. So let's try this relation, and we check for JY12. You can leave the operator sign. So JY12 is going to give us is simply equal to phi 1 JY phi 2, and that is equal to phi 1, as we know, is 1 minus 1 phi and JY, and phi 2 is 1 0. So here, as you can see, MJ dash or MJ prime is equal to MJ minus 1. MJ prime is equal to MJ minus 1. So we are going to use this case because so this case is valid, this case is invalid for that, and so we will be using this one. So we have minus h bar over 2I, and J plus MJ, as you can see, J and MJ are over here. This is J, this is MJ. So J plus MJ is 1, J minus MJ is also 1, plus 1, and the root over of that. So this is 2 times of 1, that is root 2, and that is exactly what we have, minus h bar over 2I root 2, or we have minus h bar over root 2I. We can take that as root 2, and the I taken up becomes positive, so this is I h bar over root 2. Likewise, you can obtain for other elements. The answer that I get from this is, I can take the I h bar over root 2 as common term, and we'll have 4 terms. Remember, the diagonal terms were 0, so these were 0. what I opted is this is 1, this is minus 1, this is minus 1, and this is 1. This is what I have obtained. You can check for yourself, and in case you have any variations in that, do let me know. So that's all from the assignment work on quantum mechanics. I hope it was helpful. You can fill in your suggestions or any kind of corrections that you uh, come across with or come up with while trying these numericals. It'll be most appreciated. Till then, thank you for watching.